Let's have a look at question 5 then. So we've got a rocket in space being propelled using a single pulse of laser light. When the pulse reaches the rocket, it's reflected back by the mirror on the rocket. Before the pulse returns to the laser, a mirror is placed in front of the laser and the pulse of light is reflected back. This process repeats over and over for the rocket to accelerate. So we've got laser light sort of doing, 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 doing. Okay. Explain briefly how the laser light can provide a forward momentum for the rocket. Only 2 marks here. So the first thing to mention is obviously that photons have momentum. P equals h over lambda, and when reflected, change of momentum, delta P equals 2h over lambda. Therefore, rocket gains same. Brackets, conservation of momentum. That's what we're about here. I'm not going to go further than that for 2 marks. The wavelength is given, the total energy of the laser pulse is given. That is punchy, 1.27 kilojoule laser pulse. Show that the number of photons is approximately this. So the key thing here is photon energy is hf, which by substitution we can write as hc over lambda. Therefore, for 1 photon, the energy is given by Planck's constant times speed of light divided by 403 times 10 to the minus 9. So let's turn that into a number in joules. And I've got 4.94 times 10 to the minus 19 joules, and then I just need to divide this number by that. 1.27 times 10 to the 3, because those are kilojoules, divided by my answer. Looks suspiciously like that's going to come out correct. Go away, bing. 2.57 times 10 to the 21. Job done. Whoops. Don't forget, in these, show that is approximately. Always give an exact answer. Don't just write your calculation and then say that it's equal to that. Hence, show momentum transferred to the rocket. Each time the pulse is reflected is approximately that much. So the change in momentum of the photons is 2 times h over lambda. Each photon is h over lambda, but because they are reflected, it's twice that. Delta P multiplied by the number of photons. So substitute and solve. There is another way to do this, but when you've already calculated the number of photons, I don't think it's any quicker. Okay, let's give this a go. And I've got 8.4 or 7 times 10 to the minus 6. Newton seconds or kilograms meters per second. And again, you know, to show that something is approximate, but we'll give an exact answer. So that checks out. Given the mass of the rocket, assume that the same momentum is transferred to the rocket each time it reflects the pulse. Calculate how many reflections are required for the KE of the rocket to exceed the energy of the pulse. So what was the energy of the pulse? 1.27 kilojoules. And that would have to be equal to a half mv squared. Therefore, V will be equal to 2 times 1270, twice that, divided by the mass, and don't forget to square root, which is a number. If I was a little bit slicker, I'd do the calculations in advance. But I'm not. So that's 296 meters per second. So that, I mean, are we assuming that this rocket starts from stationary? Small rocket is placed in space. So, yeah, you know, I don't see anywhere where it absolutely confirms that, but I think we've got to assume it starts from stationary. So therefore, delta V is equal to 296. So delta P, the change in momentum required, is equal to 0.029 times 296. I don't know why I've written it up there. That is it, 0.58. kilogram meters per second, and then I just need to divide that by the momentum transfer per reflection. So 8.58 divided by, did we have that number somewhere? Yeah, we have it here, 8.47 times 10 to the minus 6. Okay. I've used the divided sign there. That's a bit weird, isn't it? So, divided by, and it's a number, 1,013,000. That is how many reflections. And then final part of this question, part 3, by discussing Ke and light energy, determine whether this rocket disobeys a fundamental law of physics. Okay, that's an interesting question. I mean, the answer is going to be no. You know what I mean? They're called fundamental laws for a reason. The rocket is not going to be disobeying, so we just have to find out what's going on. So we've got like some sort of packet of photons that is going to reflect off this. Our packet of photons has this much energy. It's going to reflect, transferring momentum. Therefore, the rocket is gaining some sort of kinetic energy. Our photons bounce back at the speed of light still. This is 100% reflective, so we haven't lost any photons. We've got the same number of photons reflecting at the same speed. So what gives? You can't slow down a photon. But think about this, if I bounce light off something that is moving away from me, what I find is that the reflected light is redshifted, and therefore is going to have a lower frequency and therefore a lower energy per photon. So that's the point. Hi Laurel, that's the point or those are the points that I need to make for my 3 marks. So rocket gains KE with each reflection is true. However, reflected light will be redshifted. Each time. Hence, energy per photon will decrease since E equals HF. So what are we calling it? A packet? Are we? A pulse. So pulse loses energy. I mean, in reality, there ain't no such thing as 100% mirrors either. So you would lose some photons and you'd scatter some photons and all sorts of stuff would be going on. But I think that's the, even if we assume that our 100% mirrors are possible and that none of the light scatters and it's all kind of conserved, that's why we're not breaking any laws of physics. The pulse does indeed lose energy. So pulse loses energy equal to gain in KE of rocket. And probably you don't need to say it, but so fundamental physics not broken. Okay, and I'll stop there.